Next, let's talk about spherical mirrors. Spherical mirrors are simply small sections of a single sphere that have a reflective surface, as we talked about before. For concave mirrors, the reflective surface is the inside surface. For convex mirrors, it is the outside surface. Mirror optics problems are nearly identical to lens problems. The equations are the same. The rules for the variable signs are the same. The trends of image location are the same. However, there are a few key differences. So some main differences from lenses. First, although lenses consist of two intersecting spheres with two focal points, mirrors consist of a single spherical surface with only one focal point. Two, although converging lenses are convex and divergent lenses are concave, mirrors are the opposite. Converging mirrors are concave and divergent mirrors are convex. Third, although light passes through a lens and creates real images on the far side and virtual images on the near side, mirrors reflected light back to the near side. For mirrors, real images form on the near side and virtual images from on the far side. So, for convergent mirrors and objects outside of F, the concave mirror converges parallel rays of light through the focal point. Ray tracing the mirrors requires you to use a different strategy than that for a lens. First, light parallel to the optical axis is reflected through the focus, and second, light through the focus reflects parallel to the optical axis. The ray trace in the figure demonstrate how the image can be found and the object is located outside of the focus. And the mathematics, science, and trends showing the table is they are identical to those of the convergent lens with a object outside of its focus. And for convergent mirrors object at F, this is the same as for a convergent lens. When the object is positioned at the focus, no image is formed since the light rays are parallel and cannot intersect. However, if the object is positioned far away, the light rays arrive at the mirror will be essentially parallel. Parallel rays striking a convergent optical instrument are refracted and focused at the focal point F. A practical example of this is the collection of light from a distant star through a concave reflecting telescope. And then are the principle of objects inside of F for convergent mirrors. Just as with the convergent lens, when the object is moved inside the focus and upright virtual image is created, the ray trace rules are a bit more complicated for this scenario and are depicted in the figure. The ray parallel to the optical axis reflect through the focus as before. However, a ray drawn from the tip of the object through the focus will not strike the mirror. A new ray must be drawn. The mirror is spherical and 2F is at the center of the sphere. Any ray of light starting at the center of a sphere 2F will be reflected straight back to the center 2F. A ray of light starting at 2F and passing through the very tip of the object will reflect right back toward 2F as shown in the figure. This ray diverges from the ray passing through F. When back ray traces are drawn, they intersect to form an upright image on the far side of the mirror. No light passes through the mirror. Although this image can be seen with the eye, it cannot be projected onto a screen. It is a virtual image. And all the equations, variable signs, and imagery trends are identical to those seen in the convergent lens where the object is located inside of F. The main difference is that virtual images form on the far side of mirrors, and the table summarizes this information. So generally speaking, if you see concave mirrors, when object is outside, the focus, the image is inverted and real. When the object is inside the focus, the image is upright and virtual. And this is the simulation. Next, for divergent mirrors, the divergent mirror is very similar to the divergent lens. It is convex rather than concave. The rays trace in figure appears very different, but it uses the same logic as seen earlier. So some tips. First, a light parallel to the optical axis reflects in a line drawn from the focus. Two, light aimed at the focus reflects parallel to the optical axis. Third, the reflected rays diverge so the image is formed by their back traces, and the resulting image is upright and virtual. It is very similar to the image seen in the diverging lens. The image is always small, meaning that the coefficient of magnitude, as we talked before, is less than 1. Upright and virtual. As the object moves toward the mirror, the image comes larger and moves toward the mirror. The main difference is that this virtual image is on the far side of the mirror, and the table lists the characteristics of a divergent mirror. And if you see convex mirrors, it means it always forms a small upright and virtual image. And here is the simulation. And this is the summary of today's lesson. I used the reference book Barron's ACT Physics for today's lesson. And thanks for watching.